Hey y'all, it's Mrs. Blasky. This is the last video, the last lecture video for topic 6, kinetics. And we're going to talk about reaction mechanisms. So a lot of chemistry, like I've told you before, is telling you that what you used to know and what we taught you before is lies. So this is one of those cases. When we talk about how chemical reactions occur, a lot of times they do not occur the way that they are written down in a balanced chemical equation. Because of the way that those chemicals need to combine, because of the way that they need to collide or the orientation they need to collide, sometimes the statistics of that reaction happening, the way it's written, just isn't feasible. And so what happens is that many reactions, the way that we write them out in a balanced equation, is what we call the overall reaction. This is what we get in the end. But in order to get to those products, we might have to go through several different steps before we finally produce those chemicals. So for example, we've got nitrogen dioxide and carbon monoxide reacting to form nitrogen monoxide and carbon dioxide. This does not happen because what we find out is that instead of that nitrogen just giving up its oxygen and giving it to the carbon monoxide to form the carbon dioxide, we can actually analyze this reaction, and we notice that there's actually nitrogen trioxide being formed. There's NO3 being formed. And so we have a proposed mechanism. Lots of times we say a proposed mechanism because we're not always sure exactly what happens, but this is our best guess based on the data we can collect. That in one step, 2 nitrogen dioxides actually combine together to make that nitrogen monoxide, and then that nitrogen trioxide is what reacts with the carbon monoxide to make the NO2 and then the carbon dioxide. So if those 2 steps put together give us our complete overall reaction. Okay. So we call these elementary steps, meaning that that is the only thing going on to make a more complex reaction. We can combine these elementary steps to find out what an overall reaction is. And again, there might be more than one pathway, more than one different way that these chemicals can form. Then we might have more than one proposed reaction mechanism. So if I take these 2 elementary steps and I'm going to add them together. So if I add all of my reactants together, I get these 4 reactants. If I add all of my products together, I get those 4 products. Now, I notice that I can simplify this down a little bit. I've got NO3 on both sides of my reaction, so that's going to cancel each other out. I've also got one NO2 is going to cancel out with one of the product NO2s. And then what's left over is my overall complete balanced equation. So now we crossed a couple things out in that reaction to make this work out. So one of the things we crossed out was the NO3. So NO3 in this case is what we call a reaction intermediate. It is something that is formed in one of the steps of the mechanism, but then gets used up in a later step. And so because it's no longer around, we do not count it as a product. So those intermediates get canceled out. We also can see catalysts in our reaction. If it's something that we put in as a reactant and then it comes back out as a product unchanged, that would be a catalyst. In this case, technically NO2 goes in as a reactant and then comes back out as a product, but it's just that we're not using all of it, so we don't consider that to be a catalyst. It would have to be a totally brand new substance that does not show up in our overall equation. We also can be told or experimentally determine the speed of each of those elementary steps in our mechanism. And we don't necessarily go into specifics about that it moves this many molarity per second, but we talk about that there are fast steps and slow steps. This is another way, other than those data tables full of experimental data, that we can figure out the rate law of a mechanism or from an equation. if we can break it down into its steps. So if we look here in example 47, this mechanism has 4 different steps. And notice that it says these 3 steps are fast, but this one is slow. So just like in a relay race, you are only as good as your slowest runner. In a mechanism, you are only as fast as your slowest step. So anytime we are looking at this, the slow step is also known as the rate determining step. So our rate law is going to be written to include all of the reactants up to and including the slow step. So what that means is we look at all of our mechanism up to and including the slow step. So that's these first 3 steps. This bottom step is not going to influence my rate because basically it's going to be able to go as soon as that step before it goes. We go ahead and cross out any intermediates that we've got going on up to and including the slow step. So here I've got C being formed as a product and then being used again as a reactant. I've also got D as an intermediate and E as an intermediate. So the reactants that are left over are 1A and 2Bs. So my rate law is going to be rate equals my rate constant K. I've got the concentration of A. Since there's only one A term in that mechanism, it's first order. Since I've got 2 B terms in that mechanism up to and including the slow step, that means that B is second order. Now, interestingly, just because that is true based on the coefficients up to and including the slow step in my rate law, does not mean that that is going to be what my overall balanced equation looks like when I talk about the whole reaction. So if I go back to my mechanism and I want to know what my overall reaction is, so C, D, and E are still intermediates. To find my overall reaction, I need to look at the entire mechanism. So now if I look at the whole mechanism, including that last step, G is also an intermediate. If I add together all of my reactants, I got 2A plus 2B. And then on my product side, I've got F plus L plus M. So notice that in my overall reaction, I've got 2 A's and 2 B's. That does not necessarily correspond to those orders. That's why we can say you cannot determine the order or the rate of a reaction based on its balanced equation. We can only use that mechanism data to help us figure that out. So from a mechanism, we can get an overall balanced equation. We can get a rate law. We can see what intermediates there are. We can see if there are any catalysts in there and anything else that might be affecting how fast or how slow that reaction is going. So we're going to have a ton of problems on the AP exam about mechanisms, and we've got a ton of practice problems that relate back to mechanisms also. So we'll be spending a decent amount of time on this, and we'll see it a lot when we do our full-on multiple choice and free response practice. So that's the end of this unit for us. I'll talk to you later. Bye.